Okay, it should be fine. The only thing I am missing is charger. Okay, sorry for being late, and as I said, the next lectures I will come in the room a bit earlier, like 9:10, so don't be concerned. Usually it takes 5 minutes. I'm not teaching just for setting up everything. First of all, let me make an anticipation. Let's go to the page of the course, because yesterday, after I gave the first lecture, I consulted with my colleague Elena Toth. She's teaching the other course on water resources management. And we discussed on the background that you reported to me your background. So I decided to change a little bit the first lecture and let's say, the first couple of lectures. So I will modify these links. I will not use anymore this introduction. And also these two links, the second and the third, I'm not sure I will use them. I need to work out in the weekend the structure of the beginning of the course. For sure I will use the link on rainfall runoff modeling, because I need to get here. Rainfall runoff modeling is the first, let's say, mathematical part of this subject, of this cycle of lectures. But to get there I need to make an introduction, and I decided to modify the introduction based on what you told me. So I just want to anticipate, if you downloaded the first lecture, that I will not use them, not in the present form, and I will modify the links maybe by Tuesday. Just I wanted to let you know. Okay. So, I told you yesterday that today I want to clarify the content of this subject, the table of contents, but this is not just a trivial description, it's already an introduction to the subject. So you may want to take some notes if you wish. And even if this first lecture will be not really technical, it's just an explanation of my targets together with you, of the targets of our path that we are taking together during this subject. And let me start, as I said yesterday, let me start from the target, because I said yesterday that I would like to start from the solutions. And I would like to clarify what is the aim. Given that you are going to be professional engineers, I think it's useful that I clarify what I can teach you in terms of applications to professional engineering. So what is the role of the target of this subject, of these lectures? The target is to support the design of civil infrastructures interacting with water. So this is our target, to provide support to designing infrastructures. Structures related to water. And look, the interaction is two ways, meaning that the infrastructure impacts water, the water system, and of course the water system impacts on the infrastructures. So this is our task. So basically, what are these infrastructures? So what kind of structures I'm talking about? First of all, when we talk with infrastructures, the definition of infrastructure, of civil infrastructure, a civil infrastructure is a system that serves the civil community. It's a very broad definition. It's not something necessarily hard. It's a system. A system is intended as something that is built by humans to serve humans and to provide a service to the civil community. Means the community is divided broadly in civil and military. The civil community is the community of people living in a social context, and is distinguished from the military community because, of course, the military community has a very different purpose. Okay, and So, as I said, that the civil infrastructures are not necessarily hard structures. We can distinguish between soft infrastructures and hard infrastructures. This is a broad distinction, a broad classification. What are hard infrastructure? They are easier to define. They are something that you can touch, something that is called hard because it's something material, typically buildings or roads, something that is existing and it's material. Not just existing, but it's also material. And if I talk about hard infrastructures interacting with water, with interaction, I mean that there is a physical connection, a physical contact. And therefore we may talk about bridges, we may talk about water supply system, we may talk about sewer systems, and we may talk about check dams. Do you know what check dams are? In Italian they are called briglie, and they are transversal structures that are built on the riverbed. They are, you can assimilate the check dam to a dam, but there is a huge difference. The dam is very tall and creates a huge reservoir upstream. The check dam is no more than 15 meters tall and doesn't create a significant reservoir upstream. They are something like, if you look at, I may show you a picture, because I want to clarify what I'm talking about. Just 1 second. Okay, let me see what is the most significant. Okay, this is a check dam, and I'm not sure, let me try to, no, so this one, okay, probably it's too dark, let me see, no, okay, let me take it this way because it's clearer. So this is a check dam, so you can understand what I mean, a transversal structure which is built on a river, and this is a bit particular because there is an opening here, and usually the check dam doesn't have this kind of opening. Let me show you another picture. This is not very clear. So this is another picture of a check dam. You see that there is a central part that is lowered down a little bit, but there are no openings here. And what is the purpose of this structure is to stabilize the river profile. Because these are realized when you have erosion of the riverbed. And therefore, you understand, if you realize this structure, you stop the erosion. Because upstream you have accumulation of sediments, and this structure creates a fixed level for the riverbed. So this is the purpose. This is a structure that you can find in countries where you have two circumstances. First, slopy countries. Steep countries, countries with mountains. You can find them in the mountains. If you look at the Netherlands, I'm not sure if you have check dams there. Maybe, but you don't have really high mountains in the Netherlands, correct? Okay. And sorry if my knowledge of the geography is not so extended. And so you need hill slopes, steep rivers, and you need people living close to the rivers. Because the purpose of blocking the river erosion is to prevent landslides on the hill slopes. Because basically, if you have a transversal cross-river sections like that, the river erosion tends to lower the section down, and therefore a landslide may occur here. So basically, if you have people living here, of course they don't like it, and they want to prevent this. So basically the idea is to build a check dam that creates a fixed level here, which stabilizes the hill slope. But if you don't have in a country people living close to rivers, you don't need to realize such structures. For instance, if you go in the United States, there are a lot of mountains, but they almost don't know check dams. And they don't understand why we build them. And the reason is that they don't need to. They have a lot of room. They don't need to live very close to the rivers. If you look at Italy, Italy is almost completely covered by mountains. The only flat area is this area here where we are. It's the only one, otherwise you have mountains everywhere. And Italy is very crowded. So people tend to live close to rivers, and therefore they need to protect themselves by using these structures. And let me show you this one. I will explain you what is the purpose. This is a sequence of check dams. You see, it's a massive intervention. And this is another example. This is built with natural material, stones, because it's more environmentally friendly. And sometimes it is more durable, because the concrete, you know, when you build structure with the concrete in rivers, they are not really very durable. The concrete is not as durable as stone, hard stone. And these are built with woods and small stones. This is called ecological engineering, this application, or natural engineering structures. In Italian we say ingegneria naturalistica. Sometimes I translate in Italian because some of you are Italian, and I think if I provide the translation, the concept may be clearer, but it's something that I try, of course, to avoid. And these are other examples. This is a scheme, another example. So the subject of this course is to provide support for this kind of design. And I think this is enough to provide an example. So I was listing the hard infrastructures interacting with water. So I said bridges, water supply systems, sewer systems, check dams, fluvial defenses in general, levees, arging, or other kind of fluvial defenses. Basically, if you go over a river and you look at the river, everything is built by humans, and its material is a civil infrastructure dealing with water. And it's an art civil infrastructure dealing with water. So we need to provide support to the design of these structures. Let's now turn to the soft infrastructures. What is an example of a soft infrastructure? A soft infrastructure is a system that is not material. And let me provide you a very clear example. A forecasting system that we set up in order to predict in advance the occurrence of a flood. In Europe, we have a central forecasting system, flood forecasting system, and also in the European countries, each European country that is prone to floods has its own national or regional flood forecasting system. This is a perfect example of a soft civil infrastructure interacting not in a material way, but related to water. Another example could be a monitoring network. This is something that you can't really define as hard or soft. A monitoring network is composed by a mix of hard pieces, like gauging stations, and soft pieces, like GSM connection, or connection system in general. So I said gauging station. Let's see an example. I am Googling rain gauge, and here you can see some images, and let's take this one. This is a rain gauge. Let's see, okay. And it's from Wikimedia Commons. This is a rain gauge. And it's an instrument that measures the amount of rainfall that rains in an assigned time step. The time step can be daily. Daily means that every day a person goes there, or a connection is established to measure the water depth into this tank. And then the tank is emptied. In the past it was manual. There were people every day going there, measuring the water depth and then emptying the tank and putting again the tank there. Typically it was a job for the priorists. And this is rain gauge, as I said, but we could also see a river flow gauge. Just 1 second. This is a typical example of a river flow gauging station. It is just a meter that is placed into water, and we will see how the measurement of the water level is converted to measurement of river flow. We will see also what is river flow. I will provide definition for everything. But if you don't understand some technical term, please ask me, because sometimes some technical terms I may assume that you know, because in view of your background. For instance, river flow, I'm not sure if you mean if you know the definition. I'm sure that you know what it means. It's quite intuitive, but we will need to define it. So this is another gauging station, and the gauging stations are part of the monitoring networks. And there are several different ways to monitor hydrological processes. One is this way, the other one is by using the rowing gauge, another one is by using satellites. Today there are increasing opportunities, exciting opportunities to monitor water processes through satellites. These monitoring networks are something that can be defined as soft civil infrastructure. And the purpose of this subject may also be to provide support to the design of these monitoring networks. I just want to open and close a parenthesis. I mentioned 5 minutes ago, I said, if you go over a river basin and look around, if you look at the river, everything you see that is built by humans and this material is an hard civil infrastructure interacting with water. So basically, in making this mention, I introduced the concept of observing by you in this case. Observing is an essential part of learning, in my opinion. Learning, of course, you need to study on the books, on the web, but you need to study theory. So it's something that is done on your desk. But given that you aim to be an engineer, and you will be an engineer, a professional engineer, then you are to integrate your study with the observation. Observation builds what is called experience. And sometimes you listen to people saying you need experience, and usually these people use the word experience in a negative meaning, with a negative meaning, like you just took your degree, you know the theory, but you don't know the practice, and they say you need experience. And it seems like experience is a behavior of old people only. And this is not absolutely true. Experience is related to observation and personal practice. If you make your personal practice, you are expert. Even if you are 25, you are already an expert because you started during your degree program to look around, to make observations. And therefore, you can be an expert already at the age of 25. If one gets to the age of 80 and he didn't make any observation, any personal practice, he's not expert. So expertise is not related to the age. It's related to your capability to observe. And this is something that I think it's really important. You don't need just to study. You also need to observe. And I invite you, every time that you go around, and it may happen to you in the next month, to go over a river basin, or just planetary, and look around. Even if it seems to you that you don't really understand, indeed you are already building your experience. And indeed it should be also a task of the university, of the degree programs, to help you to build your experience. And we try to do something, but sometimes we don't have enough time. And we bring you in the labs that we have to show you how water flows. And I'm not sure I will have time to propose you a trip, a field trip, but I would like to, but I'm not sure I can, because we don't have much time. You have to take the initiative in this. So take the opportunity that the university and myself can offer to you, but also look around. Everything we study, try to look at the practice, because this should be the purpose of an engineering course, to teach you things that you can see and that you can touch, because it's professional activity. Your activity is something related to structure, to design, so it's something related to something that you can really see. It's not like studying the the nanoparticles in physics. You could see also that, but it's in our case it's easier. So I want to stimulate you to observe it. This is also why I'm showing pictures. Okay, close the parenthesis. When I said provide support to the design, I mean that we don't design these structures. In this subject, we don't get to the final design. We don't get to sizing the check dams. We don't get to sizing a dam or a bridge. I want to anticipate this, because this is an applied course, but it's not a course that ends with a design. The purpose of this course is to get to the target of the design variables, therefore providing support to the courses that should lead you to get the design. I want to say this in order to be clear and in order to explain to you why I will not tell you how to design these structures, how to size them, but I will provide to you the tools for getting the design variables. And look, this is something that is really challenging, because sizing a building is or let me say, estimating the design variables for a building is much easier than getting the design variables related to structures interacting with water. What is the reason for that? The reason is that water processes, the processes that we will try to study and to reproduce with mathematical models, are still poorly known. We don't know how water flows over the Earth's surface. We don't know that. And this is something that may sound amazing, but it's true. We see water falling in the form of rainfall. We see the water in the river, but we don't know what happens in between. So there are theories that postulate that water flows over the Earth's surface, like it flows over a roof. This is one theory, but indeed, if you go over a hill slope during a flood, you don't see the water flowing over the surface, unless it is a rocky surface. If you go over a roof during a heavy storm, you see the water flowing over the roof. If you go on a catchment on the hill slope, you hardly see water flowing over the surface. So there are other theories that say that water flows underground and reaches the river underground. But it's really strange, we cannot explain how water gets to the river so quickly if it goes underground, because underground the water flow is much slower than on the surface. So it's unexplainable how the water gets so quickly to the river by flowing underground. So there are theories who try to understand if there are preferential flows. They are called preferential flows underground, because the preferential flow takes place along some pipes, underground pipes, like in karstic areas, and therefore we could explain in this way the quick traveling of water in the underground. But still, this is a matter of research investigation. So there is a lot of uncertainty. And therefore, if you can't describe a process in detail, because you don't know how the process evolves, you understand that getting the design variables is challenging. So if I design a bridge, I need an estimate of the peak river flow, of the peak water level, because I don't want cars reached by water. How can I get this estimate if I can't describe how water gets to the river? This is really tricky and challenging. And exciting, I would say, because of course any challenge is exciting. And so our target is to provide support to the estimation of these design variables. But not everything. Okay, so basically we need to limit our attention to some of the structures, some of the design variables, because you know, there are so many structures interacting with waters. Think of a well, for instance, of everything dealing with underground water, lot of structures, or think of any surface infrastructure. So we will limit our attention to the surface hydrology, surface infrastructure. We will limit our attention to design variables related to water, to rainfall, to surface water flow, and basically that's it. We will not deal with groundwater because there are other courses in the uni here that deal with groundwater. They are given in English, they are taught in English. And therefore of course we took agreement and we are not, we try not to overlap. So basically, what are the design variables? Let me see if I'm not forgetting anything. Okay. What are the design variables that we will consider? Extreme rainfall. Not much. Extreme rainfall, let me put a plus here. And the number of pluses means the importance that I will give to each design variable in the list. Extreme floods, extreme peak flows, extreme river flows. And why I didn't say extreme peak flows, why I corrected myself. I prefer to say just extreme river flows, therefore including floods and droughts. Is it correct? Droughts? Yeah, it should be correct. Let me see. I don't remember if it is, yeah, it's GHT, not GTH. Yeah, it should be written like that. Let me check. I have a lapsus. Yeah, GHT. Okay. This is a drought. Okay. And both floods and droughts, extremes are extremely high, can be extremely high or extremely low. Both of them will be the subject of our attention. And then we will consider, usually these are point variables, unique variables. So when we talk about peak flow for a river, it's a number. And it means the maximum flow that the river can reach under certain assumptions. And we are also interested in sequences of variables, like the hydrograph. I'm not sure, probably you don't know what is an hydrograph. Basically, an hydrograph is something like that. You take a graph with the river flow, let's call it QT, let's assume that we know what is, and the time in the abscissa. This is typically an hydrograph. It's a graph displaying the river flow along time, and this is, what is this? It's the peak flow. the hydrograph peak. So the hydrograph, it's a river flow sequence. Usually when we say hydrograph, we mean something that is fairly limited in time. And the river flow sequence could be 100 years long, and usually we don't say an hydrograph in this case. When we say hydrograph, we mean something related to typically a single flood event, something that lasts maybe a few hours or a few days, but not something that is lasting 1 year. When it is 1 year, we usually don't say hydrograph, even if it's not prolonged. If you say a 10-year-long hydrograph, it's not prolonged. But usually we make a distinction between, in the literature, also international literature, between hydrograph and river flow sequence. When you say river flow sequence, usually it's not something limited. You mean something really extended. Or river flow series, or river flow time series. Is something that is extended in time. And this is also an important design variable, because sometimes just knowing the peak is not enough for designing some structures. Like for designing a dam, you need to know a design hydrograph, not just the peak flow. Because the dam is accumulating water upstream, accumulation. Accumulation needs the definition of the hydrograph. If you just say the peak flow, you don't know the flood volume. For designing a dam, you need to know the volume. Another design variable that we will consider is water level. I forgot the pluses, so this is 1 plus. Peak flow, let me put 3 pluses here. I will dedicate a lot of attention to this. The hydrograph, 3 pluses again, the water level, 1 plus. This is the kind of design variable that we are considering. Rainfall, it's extremely important because, of course, rainfall is what provokes the river flow, so it's extremely important. But on the other hand, it's something that usually it is studied in the basic courses of hydrology. And this is why I put just 1 plus. And I will keep this topic at the end of the subject. And while we are interacting, I will try to understand if you know how to estimate extreme rainfall, if you know how to estimate depth, duration, frequency curves for rainfall. And if I realize that you don't know them, then maybe at the end of the subject I will reserve a lecture on that. But it's something that usually, as I said, it's not dealt in advanced hydrology studies. And I don't really need this part to develop the other ones. You can fully understand the other ones even without knowing how to estimate extreme rainfall. So for now I'm skipping it. And then basing on the evolution of our cooperation, then at the end maybe. Okay. So these are the design variables, this is our target. And so let's go back now in the workflow that I depicted to you yesterday. So what are the kind of models I need to estimate these design variables? Every time, let me define what is a model. To me, a model is any tool, any workflow that you use to estimate your design variable. Even intuition for me is a model, is an empirical model. So let's define a model, any tool that you use to estimate whatever of these design variables. And intuition could be indeed sometimes very, very used, because sometimes you need to estimate quickly a design variable, and there are